Hello everyone and welcome to another video. So today I'd like to have a quick discussion on simple vector mechanics. More specifically, I'd like to cover these 5 topics. And I know at first blush these might seem like pretty simple topics, but we're going to see that they form the basis for a lot of engineering analysis for topics such as, say, flight mechanics or control theory. So with that being said, why don't we just jump into this? So why don't we start with this first concept here, talking about the calculating the magnitude of a vector, or also known as a 2 norm. So to start with, why don't we go ahead and let's consider a very simple vector in 3 dimensions. So let's say this might look like it has an x, a y, and a z component to it, right? It's a 3-dimensional vector, right? So if I want to know how long this vector is, or I want to know its magnitude, I think everyone will remember from elementary calculus or elementary mathematics. Well, the way you get that, right, it's you just take the x component squared plus the y component squared plus the z component squared, and then you square root the whole thing, right? So this is sometimes referred to as the magnitude, right? Or you can think of it as like the length. Or more precisely in mathematical speak, this is the 2 norm of the vector. Okay, so again, I like to just think of it as how long is this vector, okay? And again, this formula works great if you have a vector which is in 3 dimensions. But what if you have a vector in arbitrary n dimensions, okay? So we need to extend this concept of this 2 norm to higher dimensions. So in general, right, the easier way to write this, or the more general way to write this, is that the magnitude of the vector, oops, and sorry, I should have written, I got too excited here. The vector is not equal to this. I was trying to say that the magnitude, sometimes written as this, right, of the vector. So with the 2 vertical bars, that means the absolute value or the magnitude or the 2 norm, however you like to think about this. Sometimes you'll see this written with 2 bars, like this. You might even see a little 2 down here. Again, this is all very similar notation. All of these mean the same thing. They're basically just saying magnitude or the length of the vector. So again, in higher dimensions than 3, the way that you compute this is pretty simple. It's still, you take the first element squared plus the second element squared plus the third element squared plus the fourth element squared plus yada yada yada, however many elements you have, and then you take the square root of the entire thing. So in other words, a way that we could write this is you sum all of the I components from I equals 1 to n, and you square these things, right? You sum them all up, and then at the end of the day, you go ahead and you take the square root of it, right? So again, this is, for higher dimensions. So this is for A, which is in Rn, right? For an n-dimensional vector, okay? So let's just go through a very quick example. I think this is very simple, so I think everyone will get this fairly quickly, right? Let's just say you've got a vector A, which is, make something easy, 1, 2, 3, right? This is the vector A. So its magnitude, right, it's just 1 squared plus 2 squared plus 3 squared, and then take the square root of this entire thing, right? So I think if you work all this out, this is like I think it's 14 to the 1/2 or something like that, square root of 14, okay? So this is the magnitude or the length of this vector. So if you were to plot this thing out and draw a tape measure from the base of the vector to the tip of the vector, it would be square root of 14 units long, right? Okay, so that's pretty simple. Maybe what I will draw your attention to is, again, remember this formula here. And let's go with this notation with the single vertical pair of vertical bars to denote the length or the magnitude or the 2 norm of the vector, however you want to see it. Okay, because this now we can go ahead and make a comparison and go to our second step, or our second topic, namely the inner/dot product. So give me a second to erase the board and we'll get to that. Okay, so on to topic 2. So this is the concept of an inner product or a dot product. You may hear these things used interchangeably. Okay, so basically what this is, it's a transformation or a function or an operation, however you want to think about it, that takes 2 vectors going in and then a scalar comes out. So the idea is, again, you have 2 vectors, let's call it A and a B. These 2 vectors go in, and these vectors are the same length. And what this inner or the dot product operator, what it does here is it spits out a scalar number, okay? And the way that it does this operation is actually pretty simple. You'll see this written as A dot B, right? You may have seen this. Or sometimes you'll also see notation of a angle bracket B. Something like this. This can also mean inner product, okay? And what this thing is defined as, it's 0 here if A is the 0 vector, or if B is the 0 vector. And otherwise, it's basically the sum of AI times BI from I equals 1 to n, right? Okay, this is otherwise. Okay? So again, keep in mind here, both A and B are the same dimensions, right? They have the same number of elements. And again, this is all you do with the two of them, okay? So, if you notice here, this is very, very darn similar to the discussion we just had of talking about the magnitude of a vector, right? The magnitude of the vector, it was just the element itself squared, and then there was a square root in here, so it's slightly different. But I'll let you stare at this, and if you look at this long enough, you'll basically see that we could rewrite our formula for magnitude of a vector using this dot product operation, okay? So let's just make a note here that magnitude of A can be written using the dot product. Right? And if you look at that, you can basically say, all right, if you remember here, magnitude of A, the way that we got this was we took each of its elements and we squared it, and then we took the square root. So what this also can be written as is basically it's A dotted with A. Right? It's this dot product operation, but you see that we're missing the square root. So I have to take the inner product here and then take this to the 1/2. So I'm going to maybe put this in parentheses. Okay? So what this is saying is you take the inner product of the vector with itself, and then what results in that is a scalar, i.e. this scalar here, and then you take the square root. And again, the other notation that we can use just to be comfortable is, again, you may see these angle brackets, okay? So this is not, maybe tell you what, I'm not going to confuse it by talking about it too much. I'm just going to note that you may see this notation. It's the exact same thing. So alternatively, we could write A inner product A, right, with itself, and then again we have to take the square root. Okay? Okay, so that's another way to compute these, right? Now, the last thing that maybe I'll mention before we look at an example is if A and B are column vectors, right? A very easy way to make this calculation, right? If you remember how matrix operations work, right? If I'm trying to do A dotted with B, right? Which is, again, the same thing as A, B, using these angle brackets, right? That's the same thing for inner product or dot product. You see, all you're doing is multiplying the first element of A with the first element of B, the second element of A with the second element of B, yada yada, all the way to the nth element of A times the nth element of B, and you're adding them all together, right? So if A and B are vertical column vectors, an easy way to write this or to do this calculation using like MATLAB or something, or whatever you like, is you can write this as A transpose, right? So A transpose now becomes a row vector, right? It becomes like a 1 by n. And then you matrix multiply this thing with B, right? B is an n by 1. And if you look at this at the end of the day, you end up with a 1 by 1, you end up with a scalar, and it does all of the additions correctly, right? And again, the operation or the order doesn't necessarily matter, right, for this dot product, right? You could also do B transpose A, right? That's another way you could do this. Conversely, right? What if A and B are row vectors? Right? Then it's the same thing. You just got to be a little bit careful with dimensions, right? So the inner product of A and B, now keep in mind A and B are row vectors, so I think all I want to do is actually probably A by itself and then B transpose, right? Because A is a row vector, that's a 1 by n. B is a row vector, I transpose it, I get a n, oops, sorry, by 1. Yeah, there you go, right? And again, same thing, the order doesn't matter. I could go B times A transpose. right? So again, you could use this and you can use transposes and matrix multiplications to do this summation for you. So again, these are convenient ways to calculate inner products, okay? So again, let's just go through another example just to make sure with concrete numbers so we're all on the same page. Again, let's consider A, let's use the same thing we did earlier, 1, 2, 3, right? And B, let's make it kind of boring. How about 4, 5, 6? Something like that, right? Okay, so then in that case, A dotted with B, right? Or A, B, right? It's nothing more than, well, here, what is A? A is 1, 2, 3. B is 4, 5, 6, right? So you take the inner product operation. We said that maybe let's go ahead and use this formula right here to make the calculation, right? So I need to take A transpose, so this is 1, 2, 3. Here's A transpose, matrix multiplied with 4, 5, 6. Right? Okay, so now just do the matrix multiplication. You see we end up with what? 1 times 4 plus 2 times 5 plus 3 times 6. Right? So this is what? 4 plus 10 plus 18. Right? So I think you work this whole out and you get 32. Right? So there you go. So here is the inner product or the dot product of A and B in this case is just a number, a scalar number, 32. Okay? Okay, what's also interesting about the inner product is that A dotted with B, this could alternatively be written as magnitude of A times the magnitude of B times cosine of theta. And here, theta is a value between 0 and pi, right? Which is the angle between the vectors A and B, right? So I think this warrants maybe a picture. So let's go ahead and draw, like, let's say you got a vector A like this, and you've got a vector B like this, right? Now, what's interesting about this is, let's forget about this top part. Let's just look at the geometry of this diagram, okay? So again, let's assume A and B are two-dimensional vectors. They exist in the plane of this board. I think everyone will remember from high school geometry, right, that I could drop a line like this, a right angle, like this, okay? Now, would everyone agree that this distance that I'm drawing in blue, this distance right here, this length, right? Well, that's just the hypotenuse times, and here's the angle theta. Sorry, I should have written this thing theta, right? Theta, we said, was the angle between A and B. So this blue distance, right, it's the hypotenuse times cosine theta, right? So this thing right here, this length should be the hypotenuse. What's its length? It's magnitude of A. Would everyone agree? That's this distance. It's the length of this vector A times cosine of theta, right? Okay, so what's interesting is if you stare at this thing long enough, if I cover up this term right here, that's exactly what I end up with here, right? So the other way you could think about this is the inner product of A and B, it's the distance or the length of how much of vector A is projected onto B, right? That's this blue line right here, it's this length, times B, okay? So maybe what we should do is we should write that down again. So from geometry, what we see here is A dotted with B. What this physically is, the way you can physically interpret the scalar number, right? It's the length of the projection of A onto B, and then multiplied by this length of B, by length of B, okay? Okay, so again, box this up, keep this in the back of your mind because we're going to come back to this in a little while when we start talking about the scalar projection, but I think it's relevant to talk about this here because the picture goes nicely, okay? All right, so does that make sense, right? So again, the inner product of A and B, it doesn't give you this blue line distance, right? It gives you the blue line distance multiplied by the length of the vector B, okay? So we're going to have to do a little bit of multiplication, a little bit of division later on down the road, okay? All right, so while we're talking about this, let's talk about some inner product rules or properties, however you like to think about this, okay? So again, let's say you have an A and then you have a vector B, okay? And let's say you want to add these two things together. right? And maybe you're gonna maybe multiply by some scalar q1 in front of here and some scalar q2, something like this, okay? Okay, so you're gonna do this, and then what you're gonna do is you're gonna take this operation and then you're gonna dot product with some other vector c. Okay, so if you do that, you basically, what the nice property about the inner product is you're going to get this. So this is Q1 A dotted with C plus Q2 B dotted with C. So basically this is the kind of the one-shot linearity check, right? So this is basically showing that the inner product is linear. Okay, this is linear for all Q1, Q2 scalars, right? Okay, so that's one nice property of the inner product is it's a linear operation, okay? Okay, how about this? We saw earlier that A dotted with B is the same thing as B dotted with A, right? So this is like a symmetry, right? Doesn't matter which order, right? It's like multiplication, you just flip them, right? In fact, heck, it's glorified multiplication and addition, right? Okay, it's also distributive in the sense that if you have A plus B, dot product with C. In fact, we kind of saw that up top, right? This is the same thing as A dotted with C plus B dotted with C, right? Or I guess if you want to do the distribute on the left, right, you can have the vector C. Whoops, I should have had a vector at the symbol there. C dotted with the sum of A and B, right? This is the same thing as C dotted with A plus C dotted with B. And again, you can flip these orders as we just saw up here, and it doesn't really matter. Long story short, what this first property is saying is basically it's distributive. Distributive, right? Okay, here is one fascinating one. So it's what's called positive definite in the sense that A dotted with A, with itself, right? This is going to be 0 if and only if A is the 0 vector, right? Otherwise, it is strictly greater than 0, right? So this is the idea of positive definiteness. And we're going to use this fact in just a second, okay? And again, if you just remember how this dot product operation works, right, it's the sum of squares. So there's absolutely no way this thing ever becomes negative. The smallest it can ever be is identically equal to 0. Okay, so actually, you know what? Let's use some of these rules to make some interesting observations. So, for example, maybe let's come back here. I should have labeled these equations. Let's call this equation 2. Okay, in my notes I have equation 1 as earlier as kind of being just the definition of the magnitude. Okay, let's call that equation 2. So let's go ahead and combine some of these properties. So tell you what, let me, I didn't manage the whiteboard very well. Let me move some of these relevant properties to that side of the board, and then we will do a little bit of analysis. All right, so I moved 2 of our rules, the distributivity and the symmetry rule for their inner products up here. And now I want to take a moment to talk very briefly about a very famous inequality using the inner product. And this is known as the Cauchy-Schwarz inequality. And what this basically states is that the magnitude of the dot product or the inner product is less than or equal to the product of the 2 individual norms. In other words, if you have, again, A dotted with B, right, this thing's magnitude, okay, is less than or equal than the magnitude of A times the magnitude of B. Okay, again, this is known as the Cauchy-Schwarz inequality. And it is very famous, and we're going to see it's useful in some analysis. The proof of this, I think, is beyond the scope of the discussion today. If you just literally go to Wikipedia and look up Cauchy-Schwarz inequality, you'll see multiple proofs of this. So let's just take this for truth and use it for some other operations, and use it to generate, in combination with these, some other inequalities. So namely, what I would like to look at is, let's go ahead and if you recall our equation for the magnitude. So let's just say, recall the magnitude let's pick a vector, let's call it C, okay? So in other words, I'm looking at norm of C, or the magnitude of C, right? And I think we said that this was basically C dotted with itself, or inner product with itself, right? To the 1/2, right? Okay, so tell you what, let's square both sides. So I can look at the norm of C squared. So this is just the inner product of C dotted with C, right? I think everyone will agree that's fine. Okay, now let's go ahead and let C equal the product, or the sum of two vectors, A and B, okay? So let's just replace this first one here with an A plus B, right, dotted with C, right? That's the second one. Okay, so now let's go ahead and apply our distributive property of the inner product and distribute this C through, okay? So we end up with A dotted with C plus B dotted with C, right? And now we can go ahead and let's go ahead and make this replacement here of C is actually A plus B, okay? So we have A dotted with, C here is actually A plus B, right? Plus B dotted with C is actually also A plus B. Okay, so now let's just go ahead and distribute again. We'll distribute the A through this, so we end up with A dotted with A plus A dotted with B. Now distribute the B through, we get B dotted with A plus B dotted with B, right? Okay, now recall, from symmetry, A dot B is the same as B dot A, right? It's the exact same thing as we saw up there. So I can write this whole thing as, yeah, and again, we'll tell you, let's not skip steps. A dotted with A plus 2 times A dotted with B, right? That's the symmetry, combining these things, plus B dotted with B, okay? Now remember, the B dotted with itself and A dotted with itself, that's basically the same thing as the norm of A squared, right? Again, when we're taking into account that square root. So this is really, it's the magnitude of A squared, right? Okay, so this is the same thing as norm A squared, right? That's this term, okay? Plus 2A dotted with B plus norm B squared, right? That's the same thing. Okay, now let's look at this thing A dotted B. Maybe we should make a little side note. So note, right, A dotted with B, this can be negative, right? This has nothing to do with positive definiteness, because it's A and B. They're two separate vectors. It's very easy to come up with an example. I mean, heck, choose A of you know, a one-dimensional vector of length 1, choose B of -1, and you can see you multiply these two things together, you end up with a -1. So A dot B can be, it can easily be negative, right? So what happens if you go ahead and wrap this with a norm? In other words, what we can write is, I know for a fact then that if I take the magnitude of this thing can be negative. So if I take its magnitude, this has to be bigger, greater than or equal to itself. Would you agree? The magnitude of A dotted with B is greater than or equal than the A dotted with B, right? Okay, so what I can do is, if I go ahead and I replace this with a norm operator, in other words, let me write this again. So here's A squared plus 2 times, I'm going to wrap this thing in a norm, or a magnitude, A dotted with B, right, plus B squared, right? This thing down here is bigger than the line above it, right, because of the discussion we just had. So I got to change this now to a greater than or equal to, right? Okay, now if you look at this, right, recall from Cauchy-Schwarz, from, let's call it just CS, right? This term right here, this is exactly here what we had in Cauchy-Schwarz, okay? So again, I can overbound this term here by the product of the two magnitudes, okay? So again, it's still going in the right direction. I'm still making the the right-hand side larger. So what I'm going to do is I'm going to make this larger like this, too. So now instead of the product, or instead of the magnitude of the inner product, I'm going to take the product of the two individual magnitudes, like that, right? Plus B squared, right? Okay, great. Now what I can do is I can start factoring out or foiling this thing backwards, and you can see that this is the same thing as magnitude of A squared plus magnitude of b squared. Oh, sorry. No, the square is on the outside of the parentheses, right? Because if you FOIL this out, you see you end up with this exact same term, right? Okay, so again, what do we have on the far side? So this was a magnitude of c squared, and we said c was actually a plus b. Would everyone agree? That's the same thing, right? Because we said c was just a plus b. Okay, great. Finally, if we take the square root of both sides, we end up with what? We end up with magnitude of a plus b is less than or equal to the magnitude of a plus the magnitude of b. Okay, so this is another famous inequality known as the triangle inequality, right? And again, this is basically, if you want to think about it, it's basically saying that the shortest distance between 2 points is a straight line rather than going in 2 separate directions. In other words, let's say you've got, here's my vector A, here's some vector, I don't know, B, right? I think would everyone agree that, let's see, the vector A plus B, well, maybe I should draw this like in a more obvious fashion. Let's draw it like this. Here's A, here's B, right? Would everyone agree that this vector right here, this is A plus B? Right? So the triangle inequality you see right here is, what is this left side? The left side is a plus b, its length. So that's this part here. Let me draw it in. Let me maybe circle this in blue, right? So blue is this distance right here, right? This is the length of a plus this v, right? It's that vector, right? And then it's saying that's shorter than this length, which is, here's a, right? That's the length of a. That's this distance right here, right? This red thing. This is length of vector a, right? And then finally, you got green over here, which is b, right? The length of b, that's this distance right here, right? This distance is length or magnitude of b. So yeah, here's a good picture for a triangle, right? Going from here to here, it's shorter to go directly than it is to go this distance, then travel this distance, right? So that's where we get our triangle inequality. All right, so let's move on to our idea of a scalar projection. So if you remember earlier, we drew this picture when we were talking about how the inner product between two vectors a and b could be written as basically the magnitude of those two multiplied together times the cosine of the angle between them, right? And this was a picture that went along with it. Okay, so first off, I actually want to let me change notation everywhere. I'm just going to rename a and b to u and v again, right? All of this is they're just different. They're two different vectors. So again, I'm just going to change everywhere I see an A, I'm going to change this to a U. Okay. And right here, here's a U, and then this is now, I guess I got to change that in blue now. Okay, so this is U. Okay, and then I'm going to change B, I'm going to change this to the vector V. Okay, just a minor notation change, nothing hopefully too shocking. Okay. Okay, so that's a picture that we had. Okay, so now what we said is I actually want this distance, right? I wanted this distance, which is magnitude u times cosine of theta, right? So basically, if I just manipulate this equation here, we can basically try to solve for this term, which is, as you can see, just move magnitude of v to the other side, right? So in other words, what I can end up with is this magnitude of u times cosine of theta, right? It's just this thing, it's just u dotted, whoops, sorry, with v divided by magnitude of v, right? And again, this thing on the left side, right? This is literally the distance or the length of the projection of u onto v. Sometimes what that's referred to, it's the component of u projected onto V. You'll see it written like this again. So again, this is just the distance. It's how much of the vector u has been projected onto the vector v, and it's this distance, right? And you can see we now have a very convenient way to write this using the inner product, right? So this is pretty darn convenient. Right? And again, the picture that goes along with this is this quantity right here, this comp u onto v, that is this distance right here. So this is the same thing. This is projected onto v, right? That's the way you can think about that, okay? So let's just do a quick example of this to make sure we're all on the same page. Okay, so I'm going to make up two vectors in two-dimensional space. So u, let's make this thing like 1, 3, and let's make v a vector of like, say, 5, 2, something like that. Okay, so now what I would like to compute is I would like to compute the component of the vector u projected onto v. Okay, so all I need to do is just basically write this thing out. So we end up with, that's the inner product of 1, 3 with 5, 2, right? All over the magnitude of v, right? And again, we said the magnitude of v, the one way that we can get that is we can just write that as inner product of v with v to the 1/2, right? So again, I guess v here is just this vector right up here. So let me just write that in here. So this is now, let me just substitute this with 5, 2. And same thing here. This is 5, 2. Like that. Okay, great. So let's go and get the inner product of these two guys. So this, oops, sorry, that should not be a slash there. That should be like that. Okay, so the inner product of u and v, this is what? 1 times 5 plus 3 times 2, right? That's the numerator here. And the denominator here is 5 times 5 plus 2 times 2. And then don't forget to take the square root of that thing, right? Okay, so we end up with this is what? The 5 plus 6, so this is 11 on the top, 25 plus 4, so this is 29, but then I got to square root this thing, right? So here we go. This is what we end up with of the component of u onto v. It's 11 over root 29, which in numerical form, I think this is about 2.04265 or something like that. Okay? Okay, so keep this in the back of your head. We're going to, let's take one more step before we draw this out and look at this to double check to make sure that this makes sense. But this is what the calculation should get. Okay, so with this in mind, let's go ahead. How about let's keep moving? I bet we can fit this all on the board here. Let's talk about now the, whoopsies, how about the vector projection, right? Instead of the scalar projection, let's look at the vector projection, and it's very similar. It's this same picture here. Now, we've computed the length of this blue line, but what might be more useful than that is instead of the length of that blue line, let's make a vector. So I'm going to actually use, here, I'll use a different color here on the board. How about red? I want this vector here. So the red vector, the distinction here is that it has the same length as component of u onto v, right? It's this long, but it's in the direction of v, right? So the difference between the scalar projection, right? The scalar projection gives you just a number, right? It's the scalar length of the vector, right? The vector projection, I actually want a vector describing this red line, right? So you can see it's pretty darn easy. All I got to do is I have to form a unit vector in the direction of v, and then multiply it by this distance, this blue distance, right? So let me just write this down because I think it's pretty easy to see if we write this down. So if I want the vector projection, which is sometimes written as proj, so the projection of u onto v, right? This is basically a vector in the direction of v with magnitude of the component of u projected onto v, right? So, all right, to describe that, I can go ahead and say this is just the component of u onto v. That's the length of the vector times the unit vector in the direction of v. Well, that's just v all over its own length, right? Would everyone agree that this term right here is the unit vector in the direction of v? Then I just scale it up by the appropriate distance, which is what we just computed, right? So let's just plug all of this in. So component of u onto v, well, we already have an expression for that here, right? So this is just u inner product or dot product with v all over magnitude of v, right? That's the first part, times v all over magnitude v, okay? And if you want to write this in a little bit more slightly compact form, right? I think you could say this is u dotted with v all over magnitude of v squared, right? So here's the component value, and then the vector value is right here. Something like this, right? So here we go. So this is the projection or the vector projection of u onto v. Right? So again, plugging it into our example over here, we already computed the component of u onto v. So all I need is, okay, so let's do this first part. So I can write this part here, right? The component of u onto v, we just showed that that's 11 over root 29, right? Then I have to multiply this by v. V is the vector, what, 5, 2? And then I have to divide this entire thing by the magnitude of v. Where do we compute that? It was right down here. I think this term down here, yep, that's the numerator or the denominator. This thing, I think it's root 29, right? So this is root 29, right? Okay, so at the end of the day, I think this thing comes out to be, let's see, so what do we have up in there in the numerator? So this is 55 over 29. And the denominator becomes what, 22, or sorry, the second element of the vector is 22 over 29. I think something like that. And again, if you want to write this down in numerical values, this is 1.8965-ish, and then 0.7586-ish. Something like that, right? And just so that you can see all of this, tell you what, let's draw, I'll flash up a screenshot of a MATLAB plot I made, which plots out u here in red, v in green, right? And then you can see in blue is this vector right here, the projection that we just computed, right? If you plot this vector, that's what you end up with. And its length is this component of u onto v, right? And you can kind of see that the length of that blue line in the figure is indeed around a little over 2 units long, right? Okay, so we're going to see that, again, the scalar projection, the vector projection, these are very helpful vector mechanics operations that are going to help us in the future. Let me erase the board and let's go over one final one, namely the cross product. That's the last vector operation I'd like to look at. All right, so the last vector operation I'd like to talk about is the cross product. So the cross product is interesting. Again, it's just an operator which now actually takes in 2 vectors, just like we saw with the inner product. Let's call it u and v, right? And what's interesting, the cross product really has definition and meaning only kind of for vectors which are in 3 dimensions. So this should be a 3-dimensional vector, and this should also be a 3-dimensional vector, okay? And what comes out of the cross product is actually another 3-dimensional vector. So let's denote this as u crossed with v, and again, this is another 3-dimensional vector, okay? So this mapping here is actually fairly simple. So what this does here is u crossed with v. So this is how you'll see it written with an x or a times sign, right? So this is read u cross v, right? And what this is again, you get out a vector, okay? So the vector is pointing in this direction. Let's call it n hat, okay? So in this case, the vector n hat is a vector that is normal to both u and v according to the right-hand rule. Okay, so the idea here is if you have two vectors, u and v, and maybe we can kind of sketch this out, right? So you have like a u, and you might have a v, something like this. So again, with the right-hand rule, right, the engineering right-hand rule, you take your right hand, u is going to go, and you kind of make this, I joke, this is like the engineering gang sign, right? If someone flashes this as like the right-hand rule, right, you know that you're in engineering, right? So the way this works is you make this kind of three-dimensional coordinate system with your right hand, right? So u is going to go in the direction of your index finger, v goes in the direction of your middle finger, and then the right-hand rule, or this n hat, is the direction that your thumb is pointing. So in this particular case, it's pointing directly straight out of the board because u and v both live in the plane of this whiteboard. So this n hat has to be coming out of the board, right? So I'm going to draw it like this, right? N hat, it's coming out of the board. You know, alternatively, if you had, you know, in another case, you had u and v like this, you know, and they don't even have to be the same length, right? Like, let me exaggerate this, right? V could be much longer, something like that, right? So now in this case, again, u is aligned with my index finger, v is aligned mostly with my middle finger. So now n hat goes into the board, right? So hopefully this gives you an idea with n hat. And again, the interesting property about this is n hat is normal to both u and v. As you can see, n hat is perpendicular to both of these vectors, right? Okay, so again, that's the direction here. Now we got to ask ourselves, how long is this vector of the cross product? Okay, so the length of the cross product is actually going to be the magnitude of u times the magnitude of v times sine theta. Okay, so here again, theta is now the angle between u and v. Okay, so what's interesting is that you can see that the cross product here, as u and v, here's the angle here, theta, right? If theta is 0 or pi, right? If u and v are directly aligned with each other, right? What is sine 0 or sine pi? That's 0. So in that case, the cross product, it has no length, right? The resulting vector that comes out of this operation has 0 length, right? And then we see that it is maximum when theta is like, when these two angles or when these two vectors u and v are 90 degrees apart from each other, then sine of 90 degrees or 270 degrees or some multiple of that is maximum, right? Sine is either at +1 or -1 in that case. So that's when the cross product is maximal. And we'll take a look at this. I've got an animation that we can maybe look at in MATLAB in a second. But I just want to make sure we've got kind of the mechanics down. So this is the idea with the cross product. Now, the way you can compute this, there's actually an easy mnemonic way to compute the cross product, and I really like this. So the way I like to think about this is you go u crossed with v, okay? The way you do this is, again, maybe we should write this out. In this case, u and v are two separate three-dimensional vectors. So let's say that u, it's a vector which has components u1, u2, and u3, right? And same thing, v is a three-dimensional vector which has components v1, v2, and v3, okay? So the way that I've seen this done is to compute the cross product of u crossed with v, you basically draw this sort of 3 by 3. It's not really a matrix. It's not really a determinant. It's like this. You take, I'm going to put I hat, j hat, k hat. So these are sort of like the unit vectors in the x, y, and z directions, right? Then in the second row, I'm going to put u1, u2, u3. Then in the third row, I'm going to put v1, v2, v3, okay? So the way this works is that we know that this thing is going to, the cross product, it's a three-dimensional vector coming out. So there's going to be an I component, a j component, and a k component. The way you compute the I component, let's look at that one first. You basically look at, all right, I want to compute the I component. What I'm going to do is I'm going to form a smaller subdeterminant using everything that is not directly below the column of interest. So what that means is I'm going to look at these 4 entries like this. Okay, so what this is I'm going to now go ahead and write like this. I'm going to say I hat, and then I'm going to make this smaller 2 by 2 determinant. Okay, of again, the components that are not directly underneath the column of interest. So I'm going to write U2, U3, V2, V3. Do you see what I'm doing? I'm basically grabbing this smaller subblock and putting it down here. And maybe what I'm going to do is I'm going to add an explicit plus sign here. Okay? Okay? So it goes plus I hat, and then you're going to actually put a minus j hat. Okay, so now let's look at j. Okay, so now let's go ahead and erase this one, erase this. Okay, because what I'm now looking at is I am looking at the j component, or the component in the y direction. Okay, so again, to do that, I'm going to make a smaller subdeterminant using everything that is not directly below the column of interest. So it's going to be this and this. Right? Okay, so I make this little subdeterminant. It's a 2 by 2 of U1, U3, V1, V3. Right? Okay? And again, keep in mind, it goes plus, minus, and then we are going to now do the k hat, which now goes back to plus. Okay? So I want the smaller 2 by 2 subdeterminant here. Again, let's go ahead and erase this. Oops, okay, something like this. Erase. Okay, so now we're looking at the k hat term. So I'm going to form a small 2 by 2 determinant using the submatrix of elements which are not directly below the column of interest. So that's these two over here. Okay, so this now becomes U1, U2, V1, V2. Okay, so again, a couple of gotchas. Remember, it goes plus, minus, plus. I guarantee you someone is going to mess up this minus sign. They'll add a plus sign, and you're going to get some weird cross product. So keep in mind, this is always, again, this is going to be the minus, okay? All right, so let's do one more line, and actually I'm going to give myself a little bit more room over here. So this is now I hat. Now, all this is, it's a 2 by 2 determinant. I think everyone remembers how to do a 2 by 2 determinant. It's this times this minus this times this, right? So it is U2V3 minus U3V2, right? That's this term. So this thing here is basically this thing in parentheses, right? Okay, then we go. Okay, now let's do the next one. Minus j hat, right? Okay, and then I got to do this determinant here. So it's this times this. It's U1 times V3 minus U3V1, right? So again, this determinant is this term right here. And then let's do our last term, plus k hat. And then it is U1 V2, so it's U1 V2 minus U2 V1. So again, this 2 by 2 determinant is this term in parentheses. Okay, so here we go. Here's the x component, the y component, the z component, right? Or the I hat, j hat, k hat components. So if you want to write this as a 3 by 1 vector, you know, you're more than welcome to, right? You can write this thing as basically U2 V3 minus U3 V2, right? And then it is, you got to be real careful about that. Again, be careful about this minus sign, right? This now has to be, what is it? It's U3V1 minus U1V3, right? And then the last one, it's U1V2 minus U2V1. There we go. So here you go. Here is how you can compute U cross V. And I don't think there's any need to go into an example because literally here it is. You have a vector U and V with these components. This is literally how you compute the cross product. right? So tell you what, let's just go back, let's jump over to MATLAB real quick, and I want to show you an animation that I made showing how the cross product changes as U and V change. All right, so here's a real simple animation I made that just computes the cross product of U. U is red there, and V is the green vector, as you can see, that is kind of moving around in this arc. And the blue vector is just basically the resultant cross product of U crossed with V. So as you can see, if U and V are aligned or completely anti-aligned, the cross product is 0. But when they're perpendicular to each other, like there, you see that the cross product is maximal. And again, we see that the direction of the cross product is again normal to both of those vectors and in the direction of the right-handed rule. So this is just a quick animation to show how this cross product changes as U and V change. All right, so with that animation now, hopefully we have a better feel or a physical idea of how the cross product of these two, or how the cross product of two vectors change as the geometry between the two vectors vary, right? So again, the other thing to keep in mind, right, remember, the cross product, you have to feed it of two vectors and it spits out another vector, whereas with the inner product, right, you feed it two arbitrarily sized vectors and it spits out a scalar, right? Actually, related to this, now might be a good time to introduce a ridiculously bad, corny math joke. What do you get when you cross a mountain climber and a vector? Nothing, right? Because you can't cross a scalar with a vector. Get it? Right? Okay, anyway, so, with that being said, with that horrible joke, maybe this is, I'm hearing the groans. I think it's probably time to wrap this up. I hope you enjoyed the discussion today. This was a very brief introduction on some simple vector mechanics, but you're going to see that we're going to apply a lot of these tools to our subsequent discussions, and I hope you'll join me at those. For example, in our very next lecture, we're going to use some of these tools to derive some rotation of a vector formula, as well as apply these to things like rotation matrices and different frames of references. So this mathematical framework is going to serve us well as we move down our discussion and analysis of different engineering topics like flight mechanics or control theory. So yeah, like I said, with that being said, I think it's probably a good spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. And remember, the new videos come out every Monday, so I hope to see you at one of these future discussions where we can all learn something new together. So until then, I think I'll sign off for now. Talk to you later. Bye.